So, the part two of this lecture, which is about the process manager. So, we discussed the process. I mentioned what um, task is and what also the thread is. So, the operating system needs to keep track of the process. I said that what is process and task is the static part, thread is the dynamic part of that. But when we use multiple processes to run the programs, we need to be able to track them. So how to track that? As you may remember, I said that and I show you that we have something which is called process control block to represent the different objects it's dealing with. The data structure, type of the data, because in each portal we've got data. The program process control block consists of the task, represent the task, data structure task, which is the resources allocated, and one or more threads or a control path through the code. So it means that we've got the resources that we need here. Also, multiple threads can link to that. It must be possible to represent the one task and a variable number of threads. As you see here, we have two threads there. It's a multiple thread. It needs a static part for multiple threads and a dynamic part which can grow or shrink because we can have one or more than one thread. So this is, in terms of, as I showed you before, this is this data structure that represents the process, or it's called process control block. So let's look at inside of each part. Task structure. So the structure of the static part, almost similar to most of the processes, contains this information. What are they? Owner, which program actually is the owner of that. Who is the owner? We've got something which is called unique process ID because we've got to be able to track the processes. Address space. We need to know the addresses of the programs that are running and where they are in the memory. The stack addresses, data starting addresses, program starting addresses. We've got to know the location. The location is important. How many threads it's got? Number of threads. List of the threads. Directory and open file information. What is the information of the file that is running here? So this is the static part which doesn't do anything. It's a resources for the threads. And in each time, when you have single process, all this information should be saved and reload. And as you see, you don't need to change any of them, for example, for single process. So because of multi-threading, save the time and the energy to save and reload the same data. What about thread? Thread structure is something like this. The task to which I belong. What is the task? You've got to actually have a place to actually save this information. List of threads in the task. Volatile environment, I will explain that shortly. State, what is the state? Again, are we in the running state, waiting state? What is the situation? We've got to save it here. The links, the priority, does it have any priority? Because I will explain that maybe it's better to run certain number of threads first and then run the other threads. So we need to know about the priority of the threads. So one of the more important fields in the thread structure is the volatile environment, as I mentioned here. What is volatile environment? As I said, that I will explain that shortly again in more details, that when a thread is blocked, we've got to save some information regarding that specific thread. So we save and load that in the volatile environment. We don't need to save the whole picture again for the whole process. But what we do in the multiple threading, we actually save the state of this part, of that specific thread at that time. So we use this in this place, which is volatile environment, that actually save the information about this stack pointer, where is in the memory, registration, registers, and program counter, and the program status register. These are the type of register that can be used. We explained a couple of them in the CPU lecture. So what happens is that this is the structure, but this volatile environment actually save the current situation. When you want to save the thread, when any block happens, when anything happens, you need to actually wait this thread. The current information of the thread will be saved in this place, which is important. So I talked about the state here, as you see. What is the state? We need to know. We've got two types of states. One of them is run, the other is the wait. Run, what is run, what is wait? The state of thread is at any particular time is recorded in the state field of the thread structure I mentioned here. It's recorded in the state part there. We've got two types of states. One of them is run. It means that when we running the states, running the threads, it's running, it's ready to be executed. So as you see, the ones that are ready to actually be executed go to the run queue, and they are waiting to go to the CPU and get the time to go to the CPU and to be processed. The other one is those threads that they need to wait. For example, you want to print something. That process for printing, that thread for printing is waiting for you for the pressing enter. Because if you don't press enter, it doesn't print. So what happens? It goes to the wait queue and waiting for an event to occur. As soon as that event occurs, actually it goes back to the run queue and goes to CPU to be executed. I will explain that more. So when a new thread is created, immediately go to run queue. It always begins in the run state on the run queue. It goes for the run in the thread structure. The state will be run, and it will be given some time to be executed on the CPU. This is the scheduler job to actually say, okay, this is your turn. You go to the CPU. No, you've got to wait. This thread should wait. The first one should go. We don't have capacity there. There is no time there, so you've got to go first, use second, and so on. We will discuss this scheduler, how it works. But as soon as the thread is created, it goes to the run queue and is waiting for the scheduler to get a time to go to the CPU. So a thread may stop using the CPU for three reasons. For three reasons, these threads in the run queue may actually don't go to the CPU and wait. One of them is when they are in wait state voluntarily, that they are waiting for an event to occur. So, for example, a thread come here for printing, but because it's got to wait for event to occur, it goes to the wait queue, and as soon as that event occurs, it goes to run again and go to the CPU to be executed. Termination. When you terminate, for example, you want to by force stop a process. What happens? You terminate that. Actually, we stop that. The other one, which is important, is preemption. Operating system takes the processor from a thread. When a thread has used up its share of time, or when the CPU is needed to handle some more urgent work. For example, so a thread is created, it goes to the run queue, and it gets a time priority, whatever from scheduler, goes to CPU. But as soon as it wants to be executed, something more urgent happens. So what happens? You've got to return it back to the run queue and say, okay, you've got to wait. Something more important is happening. We've got to wait for that. It may go to the wait and come here, but preempt is when something actually urgent happens. It goes back here and again will be run in CPU. A thread leaves wait state when an event it's waiting for occurs that I mentioned. So when it's wait, we've got to that event happens to execute. So I was talking about this wait and run. So this context is switching. We call it context switching, which is important. The whole procedure of reallocating a processor from one thread to another one. It consists of two things. A context switching is called when a thread loses control of the processor and moves into wait state to wait for a resource to become available. So here, when something comes here, but it needs an event to occur, it goes to the wait queue. So context switching happens here. It actually switches the context to wait from run. Or an time interrupts to tell it's used up and actually that it's used up its time slice. The time has been used up for a process and nope, you've got to change. You've got to go back or preempt, go back to run queue and run it again. So at these two times, the context switching happens. When context switching happens, as you can read from here, we've got to save the state of that specific thread. Where do we save that? Save that in the volatile environment that I explained. All of those changes happens and should be recorded in the volatile environment within the thread structure. So we use context switching between run and wait. So I was talking about the scheduling, thread scheduling. What's that? The main purpose of the scheduler is to see that the CPU is shared among all the contending threads as fair as possible. What do I mean as fair as possible? It means that you've got to bring down the response time because we get bored. If you want to run a program, it takes long. So what happens? The CPU should be quite efficient to run the most important one first and run the rest in a good way to be able to handle all the threads and the threads. So in the real-time systems, the scheduler will have to be able to guarantee that response time will never exceed a certain time. As soon as this certain time actually passes, it will be preempt, specifically it will be preempt, goes to run queue again, and will go back to CPU. So that's very important to bring down the response time. How we do that? We use that in there are loads of other techniques, but I'm telling you the most basic and the fundamental ones. Thread scheduling and thread priority and thread multi-level priority queues. What are they? So what we've got to do, if we don't have any priority in terms of our threads, the first one who comes should be executed. Second one, next. So it's called first come, first serve. But if, sorry, if the one of the first one, actually it's not important and use the whole CPU, the most of the CPU, it's not good. So an urgent thread should wait on that queue to actually wait to get some time to go to the CPU. So it's not good. We need to prioritize that. What to do? What we do, we actually put more priority threads at the top of the head of the queue. The priority is allocated to thread when it's created. So when we create the thread, we put some priority. If you remember in the thread structure, there are 3 places to actually mention about the priority. What is the priority of that? So when you get a priority, you have run queue and wait queue. You put the descriptor of all runnable threads are linked into the run queue, ordered by decreasing the priority. You put, for example, thread in this way. The one that's got the highest priority, you put it on the top. The rest will go to waiting queue. As soon as they are actually the more important ones are executed, then the wait queue will actually come to the CPU and will be executed. So run queue is based on the priority. The most important one goes first, and the rest, less important, or there is no important difference between them, goes into the wait to be executed. Again, they are based on the decreasing priority index, let's say. This is thread priority when we have only priority in one level. Important, not important. But sometimes we've got different layers. We've got high priority queue, low priority queue, and wait queue. How it works? It's got thread multi-level priority queues. So When a thread is created, it's initially put on a high priority queue. Initially, whenever a thread is created, we said this is high priority. So if it uses its full time slice, this implies it's compute bound. So when it is context switch out, it moves to the tail of the low priority queue. What it means? So when a thread is created, it gets the high priority queue. It goes to CPU. If anything happens, actually it used all his time, it means that it's not that important. Because if it was important, we had to actually run that, it would be executed. What happens? It goes to the low priority. Actually, the scheduler brings it back to the low priority. And that happens. So the high priority goes, and then the waiting queue will be called by the CPU. Then the low priority. So on the other hand, if the thread gives up the process to wait for an input-output event, for example, then it can be assumed that is interactive. Then, when the event is waiting for occurs, it's moved from wait queue to the high priority queue. Threads on this queue are always offered the processor before the low priority queue, but are expected to keep it for a shorter time. It means that, first of all, we run them. If we see that there is any problem with them, it's not important anything, we put them in the low priority. We get the other threads from the wait queue, not the low one. When the wait queue finishes, then we take these threads which are in the low priority. So, guys, what I did, I finished the this part, Process Manager. You can read the chapter 2 of this book. I will scan that and put it on the Moodle. You can read that, and I hope that it was clear. And if you have any question, you can contact me to ask your question. Thank you very much, guys.